So, coming back to different coil designs, so this is an animal coil design. So this is for rat experiments. Again, in rats, the regions are very small, so your focality should be of the order of 1 or 2 millimeters. So to get that small focality, it's very difficult with any type of coil. So you have to use a core, and we are using a permanent core. It's cobalt, vanadium, nickel alloy. So permanent has very high relative permeability as well as high saturation. So we use permanent for that. And again, for shielding, obviously people would say, oh, use permalloy, right? But the problem is if you use any high relative permeability shielding material, so what do you think will happen? So if you want to shield other regions of the brain and just focus the flux to a small area, if you use a permalloy, what will happen? Well, a lot of the flux will flow into permalloy, but that will decrease our flux in the ferromagnetic core. So because of that, we used a diamagnetic plate which has very high negative susceptibility. So this is pyrolytic graphite. So when we use a diamagnetic plate, so this is what we find. So this is a misnomer, multimagnetic material coil. So diamagnet is not a magnetic material. But anyway, so this is the figure of 8 coil. You see how broad is this? So the area of stimulation is quite high with this one. And our PFC is this purple area. And when we use a diamagnetic plate, we get narrower, higher focal area. So that means we can stimulate a much smaller region of the brain. So you can see the difference here. So this is actually, we published just the design, now we are fabricating it for animal studies. We have animal studies ongoing. We used other core to look at other effects. I can talk about that later. You stop by. So these are all different coil designs that are in the works. And there are not many people who are doing coil designs. There is actually a large need for new coils. We are doing some of our part. So now that brings us to, so if you're doing coil design, so I say that the most widely cited paper was using a sphere as a head model. And before that, people used standard anthropomorphic head model called SAM. So basically it's a head shape, but it's all homogeneous. But if you look at the induced electric field here on the surface, it's from the homogeneous head, you get this nice pattern. But if you actually build a head based on MRIs, you take the MRI and segment the skin, skull, CSF, that is cerebrospinal fluid, gray matter, white matter, ventricles, and then build a head model, volumetric head model, and assign different electrical conductivities to all these regions. They have different conductivities. The magnetic permeability is close to 1 for all these regions. So you can put close to 1, but because the conductivity is different, the induced electric field will change depending on the heterogeneous electrical property, the heterogeneous conductivity. Although we don't have to consider permittivity at this point because we only, our signal is only 2.5 kilohertz. So it's a low frequency signal, so you can ignore the permittivity part. So if you use a heterogeneous head model, this is how when you calculate the induced electric field, this is how it looks. You can see that there are some regions that have higher induced electric field, compared to the regions that are closer to the coil. So it's not homogeneous like here. So it is essential that one needs to use heterogeneous head model if you want to design an accurate TMS coil. So that's what we have done. So when we, this is from a commercial head model. We paid quite a lot of money to get this head model. So this is the B field, H field, and this is induced electric field using a standard double coil or a figure of 8 coil. So now here are different head models. So if you use just homogeneous head model, standard anthropomorphic head model, if you look at E field in the z-axis, so it decays rapidly, homogeneously, or it's a nice decay. Whereas if you look at the heterogeneous head model, these two both are heterogeneous head model. This is from standard anthropomorphic head model that you saw in the previous slide. So if you use a heterogeneous head model, the decay is somewhat irregular, although the overall decay is similar, but you have regions in between that might show higher induced electric field compared to the regions closer to the brain. You can see that here, although this is further away from the coil, but it has higher induced electric field. And we consider 150 volts per meter on the motor cortex as the threshold field that initiates an action potential. So if you want to make a twitch in the thumb, you have to depolarize, you have to make the neurons fire, right? And that firing in electric field on the surface of motor cortex is about 150 volts per meter. So anything above that is hyper activation. So, and then what we showed here is, we showed for different age group. So this is a head model of a 34-year-old person. This is a 26-year-old person, 11-year-old, and a 6-year-old child. So you can see the 11 and 6-year is the blue and the pink. So they have irregular decay rates, whereas the 34-year-old person has a somewhat closer to the homogeneous head model decay. So that means when you are treating different people, you can't just scale your dose rate. That is, so the way the treatment takes place is you determine for a specific person what is known as resting motor threshold. So you put the coil on the motor cortex that stimulates your thumb, and you connect the thumb to an MEG, that is, it records the myogenic signal. So when you start stimulating, the moment you record 50 millivolts, why 50 millivolts? Again, that is from the electrophysiological studies. So once you hit 50 millivolts, that's when the neurons in the motor cortex corresponding to the thumb depolarize. So that means that's when they hit 150 volts per meter. So different people have different resting motor threshold. Yeah.
And how many people did you do this study? Like only 4? Or?
So this is the model. I'll come to the clinical studies a little later. We are still looking at the models here. So this is 34 here, this is 4 head models. Yeah. So again, we have built a lot of head models. When we were building head models for individual subjects, those were so new. Back then, one of the medical companies, Zurich MedTech, licensed our models of 50 healthy head models. They were free for research purpose, but you had to pay a licensing fees if you were a hospital or a commercial company. Since then, nowadays there are tools. It's a pipeline. You get a pipeline. You can take MRI and then use certain tools. Back then, we were connecting different tools and build a volumetric head model and assign these electrical conductivities to different regions to build these head models. But nowadays, there are tools available, so you can take MRIs and build head models. So we have over 1,000 head models in our data set now of different disorders, different age group. So now we have computational head models, we have coils, but now we can't go on to the human subjects, right? Even for animal models, we have to have an intermediary step. So we had to test them on some physical phantoms that show the geometry of a brain. So when we looked the commercially available brain phantoms, they were there for imaging purpose. These are NIST developed MRI phantoms. So we decided to build our own anatomical models. We had a lot of head models. We decided to use 3D printing. So basically using some rapid prototyping technique wherein you create shells with certain volume, and then these shells can be dissolved, and you use a polymeric material in these shells and dissolve the shells, and you are left with the structure. And this is PDMS, and it's not conductive, so we had to make conductive polymer composite. So we used carbon nanotubes with PDMS to tune the conductivity of our different layers. So right now we have gray matter, white matter averaged layer, but we think we can build a phantom that has multiple layers with different conductivity. So and then after we fabricated the phantom, we had to test it, whether it is anatomically accurate or not. So we can't take the MRI image of the same phantom because it doesn't have water molecule. So we had to take CT scan of the phantom and match that with the original MRI. And there are some mismatches, but those are because how we place the phantom in the scanner. It's very hard to reference the coordinates. So here is the overall schematic of how we made the brain phantom. And you can see this from this publication. And then we measured the voltages for different TMS strengths and at different distances in the phantom. And this is the signal from the phantom. So if you just put an electrode below or just a wire below the TMS coil and measure the voltage, you get this nice, not completely symmetric, but nice waveform. And this is what you find in a phantom. This is a reference. If you just put it outside, this is inside a phantom. And we measured the voltages, and it confirms our simulations. So now we have built a brain phantom where we can test stimulation strength in the form of voltage at different levels. So while we were doing this, a neurosurgeon at VCU, who does a lot of deep brain stimulation surgeries, she has 2 surgeries a week. So she does 2 surgeries a week for treating Parkinson's patients. So DBS is a well-established technique for treating Parkinson's patients. Basically, there are 2 electrodes on both the sides. They are inserted, and the tip of the electrode stays at an area called subthalamic nucleus, STN. That's where the dopaminergic neurons are there. So when the dopaminergic neurons die, there is low dopamine, and low dopamine in that area causes the motor pathway network to go imbalance, and that's what gives you tremor in a Parkinson's patient. So they use these deep brain stimulators to stimulate the STN area, which balances the motor pathway network and reduces the tremor immediately. So this is done with using by surgery with this lead, and here is a power unit that continuously sends a small current, and this needs to be charged regularly. So this is a well-established technique. So the surgeon with whom I collaborate, she claims to have done 1,000 such implants bilateral, so 500 such surgeries. So she works for Richmond Veteran Affairs Hospital as well as VCU Hospital. So she's a famous neurosurgeon in the East Coast. So here is a short video showing how the DBS works, deep brain stimulator works. Right. So, so that is DBS. I have attended. I've attended 2 such surgeries. It's amazing to watch. When they are inserting the lead, the person is awake. They only anesthetize the person when they drill the hole on the skull. But when they are inserting, they insert millimeter by millimeter, and there is a CT scan that is constantly showing where the lead is, and every millimeter they check whether the person is having all the functions. When they ask the patient to move different parts of the body, and the neurosurgeons, they know how each neurons fire, so they literally connect the DBS lead that they are inserting to a speaker. So when the neurons fire, you can hear the firing pattern. And the neurologist, he has worked for, he's the one who is doing that studies, he has worked for 30, 40 years, and he knows exactly where the lead is. Oh, that is subthalamic nucleus now, that is firing the pattern, just by listening to the speaker. So it's a well-established technique. It used to be $100,000 US per surgery before, but now it has become slightly cheaper. So this neurosurgeon, Catherine Holloway, so she's the one. So she asked me, because her patients develop, after about 5-10 years, they develop speech impairment. They don't know whether it is because of continuous stimulation at STN, or it's just natural progression of the disease. So they have difficulty in talking and swallowing. So she wanted to do, because the mouth motor is on the cortex, so she wanted to do TMS on the mouth motor area. And if she has to do TMS on the mouth motor area, there are already 2 leads implanted in this brain of the Parkinson's patient. So she wanted to know what is the electromagnetic interference, EM interference, between the TMS coil and the DBS lead. So we had to design to the DBS dimensions. We designed this DBS lead. We did the computational study first. So we applied TMS on the mouth motor area, and we looked at what are the induced currents on the lead as well as on the different areas of the brain. And also we looked at if there are any temperature changes or Lorentz forces due to AC fields. So the Lorentz forces and the temperature, there is no observable changes at all. This is the temperature map. No observable changes inside. Again, the diagram you see here is, look at this, from very dark to very bright is 0.5 degrees centigrade. So that's within the limit. So we looked at different region. So when we apply TMS field on the mouth motor area, so on the mouth motor area you have high induced electric field for different intensities. So you need about this 3000 amps, about 150 volts per meter. That is the threshold E field. But if you look at other areas, they're way below 50, even at the 100% of the TMS output. So, which means it's safe when you look at E fields. We stimulated different regions to look at the safety. And then we wanted to use our brain phantom to measure the same current when you apply TMS on the phantom that has DBS leads. So we did that, and then so here is, this is the current in the DBS lead. So this is milliamps. So you have about 3 milliamps at 100% intensity, which is 5000 amps. in the stimulator. So at the 100% stimulator output, the 3 amps is similar to what they use for stimulating SDN area. So at the 100%, you at most what you do is you stimulate SDN. But there are no unsafe currents in the DBS lead when you stimulate. This is when you put it right on the top of the coil. But if you are on the mouth motor area, this will be much lesser. We concluded that it's safe to do TMS on subjects with DBS. And then later on we found that there are several people who have done this without having to think about, without looking at the EM interference. And then we also built brain phantoms for animals, and here we were looking at the induced electric field with different type of coils. These are ferromagnetic cores. One is, I think, silicon steel, another one is permanent. So this is Wesley's work. So he uses triaxial dipole to measure induced electric field. Basically, he measures the voltage at these 2 points and divides it by this 3 millimeter to get the induced electric field. But he does it on all 3 axes to get XYZ component. This is very difficult measurement because you had to have really nice amplifiers and good setup, basically, which we used at Harvard Medical School. This is on the animal phantoms, and again, we compared our induced electric field measurements to the saline solution and our simulations as well. So they agree with each other. So now I want to talk a little bit about human subject studies. So we did 3 clinical trials. One is on the healthy subjects, another one is on schizophrenia patients, and another one is on traumatic brain injury patients. So in the first one was healthy subjects. We recruited 10 subjects, and we were looking at how the variation in the anatomy of the brain, that is the brain scalp distance, the distance from the scalp to the surface of the brain affects the TMS response. That is the twitch in the thumb, which is measured by RMT. And why RMT, the twitch in the thumb intensity, is important? Because that is the dose. So if you go for TMS treatment, if you want to stimulate the executive part of the brain, they don't know how executive part responds until 6 weeks, right? So in order to know what is the dose level for that region, they first apply the TMS on the motor cortex, the thumb area of the brain, and the intensity at which your thumb twitches or gets 50 millivolts is RMT, and that changes from person to person and from day to day. If you did not have good sleep, or if you had coffee, alcohol, medicine, it all affects your dose, which is RMT. So we wanted to look at how RMT changes with the anatomical features of the brain. We recruited these 10 healthy subjects, and this is how we measured the thumb twitching EMG sensor. So that is the myogenic signal that we measure in the form of millivolts. And again, we looked at different protocols, which is called IPBS, but I'm not going to talk about that. So before I go in depth into the results, so the motivation to do the clinical trial comes from our previous study where we were looking at how the anatomical features influence the induced electric field. So here we used a public database. Basically, we took MRI images that were published and built head models. So these are of 50 healthy and adults, so below the age of 36, above the age of 18. So we built head models of these 50 subjects and calculated their induced electric field for different intensities, and we looked at how the induced electric field, this is the maximum, for maximum intensity, the induced electric field as a function of brain scalp distance. So we see that as the brain scalp distance increases, the induced electric field decreases. And if you look at the volume of brain, so what happens is, again, in another study, as people age, there is brain atrophy. So the size of the brain decreases a little as people age, and the brain scalp distance increases. So the older people will need higher stimulation intensity. And when you increase the stimulation intensity to get that 150 threshold volt per meter, you end up, because you are increasing the intensity to have that threshold, you end up stimulating larger area of the brain. And when you stimulate larger area of the brain, you are more likely prone to induce seizures. So it is important to know the brain scalp distance, or important to determine the dose in the form of RMP. So this is what it shows. So as the percentage, as the brain scalp increases, the percentage of the brain volume stimulated increases for 150 volt per meter threshold E field. So we also looked at, this is again coming from public database. This is for Parkinson's patients. This is 20 head model, 20 patients, and here also we see the same. This is, because this is Parkinson's patients, these are older patients or older subjects. So here we see that as the distance increases, the induced electric field on the surface of the brain decreases. So this is for established models. We have it for all these head models as well as established the commercial head models. So here the volume of brain stimulated above 50 volts per meter also decreases as the brain scalp distance increases. So with that background, we wanted to look at what are the parameters influencing